Okay, let's start a quick review on the charge and discharge of capacitors, so the RC circuit. One very important characteristic of the RC circuit is that when you put a resistor and the capacitor together, and of course the battery to charge the capacitor, even a battery, which is a DC battery, the capacitor starts charging up or discharging when you remove the capacitor and put it in with the resistor. The current in the circuit and the voltage change as a function of time, and also the charge. So this is an interesting characteristic of the RC circuit that we will review very quickly here. So the first thing, we will start with charging a capacitor. So when we put a capacitor with a potential difference, let's say so with an EMF that has a potential difference E, let's say I have a switch here, and then I have potential capacitor, and then a resistor R, okay? So at T equals 0, when I close the switch, this is a switch S, when I close the switch, the current or the charge in the capacitor is equal to 0, because the capacitor just start to charge. So at T equals 0, the charge in the capacitor is equal to 0, which means the potential difference, I will call it, this is A, this is B, and this is C. So the potential difference across BC, which is the capacitor potential difference, is equal to 0. So, and then the interest here is to look at what happened as a function of time. So we can easily look at, let's say the current is this way, and we can have Kirchhoff's law. This Kirchhoff's law will give me E minus IR, potential difference across. So I'm going through this loop, and minus VBC is equal to 0. We know that V across the capacitor is equal to the charge as a function divided by the capacitance, right? So this will give E minus IR minus Q over C is equal to 0. We also know that the current is just the rate of charge. So I get then R dq over dt minus Q over C is equal to 0, which is a differential equations, a first order differential equations, that I can do R dq over dt is equal to E minus Q over C, or I can also, this gives me dq over dt is equal to E over R minus Q over RC. We can also do dq over dt is equal to EC minus Q over RC, and I can bring EC minus Q here, and then dt over RC, and I can multiply by minus 1, which gives me dq over Q minus EC is equal to minus dt over RC. This is the equation that I want to integrate. Obviously, the first one will give me an ln, and this one will give me a time. It's a constant. So to integrate, I am integrating from the moment the capacitor starts charging to any moment that the charge has a value qt. So this integral will give me ln of Q minus EC minus ln of minus EC is equal to minus T over RC. And Q minus EC minus EC is equal to minus T over RC. Obviously, I can get rid of ln by putting everything to the exponential, which will give me Q minus EC over minus EC is equal to exponential minus T over RC. And this will give me the charge as at any moment, the charge at any moment that is equal to EC 1 minus exponential T over RC. This is the equation of the charge. Now, the maximum charge is this one. So the Q0 or Q max is EC. This is the maximum charge that the capacitor will reach when time goes to large values. So after sufficient time, the capacitor will get Q0 equal epsilon C. And you can also see that the current, which is the derivative of the charge, the current will give as E over R exponential minus T over RC. So I0 is equal epsilon over R. Okay. So those are two important equations of the charge. So the capacitor is being charged until a maximum value, but as you can see, the current is decreasing, and after sufficiently large time, there will be no current flowing into the circuit. So if you want to plot qualitatively what happens to the charge, so what happens to the charge is epsilon C. So you can see this, and what happens to the current? What happened to the current is the opposite. It's a decrease, exponential decrease. Okay. So thank you for your time.